sense or you're not sure what it is that we're doing, please let me know and we'll see where we go on from here. And so we'll have an assignment or something else, reading assignment and things to go on with respect to curing. But I thought we should have a discussion of what curing is and why we care about curing the concrete. And I used to put up, I had a poster made up in my office in Ottawa some 30 odd years ago, which said, I have to cure the concrete. I didn't even know it was sick. And of course, curing in this sense does not mean healing. Curing in this sense means providing the conditions that will cause the chemical reaction that we're relying on to make the concrete have strength to continue. And let's see if we can make it happen. Maybe we can't. All right. This curve shows us aspects of the concrete as a material and what happens to it with time. And so we've had some discussion of this. That is, we're talking about rigidity or how much of the material is a solid. That's here, I'm sorry. And then at some point, as it stiffens and as the chemical reaction of the hydrating binder takes place, we reach a point where we can no longer handle the material, where it has become a solid. That solid has very little strength, but it's become a solid, and we refer to that process as setting. We get an initial set, which we arbitrarily decide is where the pin penetration, if you push a pin into the concrete, it takes 500 psi to push it in 1 inch, and a final set where we're at considerably higher stresses than that, depends who you talk to. At some further point, the material becomes rigid. It becomes a solid with some strength. And that process takes time, and that process is dependent on, among other things, the environmental conditions. For example, if we were to look at a structure that's being placed at very high temperature, then we would anticipate that it would set and gain final set faster than one if it was placed at lower temperature, because it depends on the rate at which our chemical reaction is occurring. And we should know that so long as the concrete is exposed to the environment, it is possible, and in fact is foreseeable, that drying is going to take place. Drying is in the first stage, refers to the water that is lost from the surface. And it's lost by evaporation, no different than if you were to put out a bowl of water that in a room that's not at 100% relative humidity, that the water would evaporate and go into the air until all of the water was gone. And so our concrete, in this particular case, represented by this figure, has a certain amount of water that's sitting at the surface. As the particles fall, we'll see a sheen of water appear, called bleed water. And if that bleed water is exposed to a high evaporation rate, a hot, dry, windy day is worse than a cool, high humidity, non-windy day. In other words, the temperature, the relative humidity, and the airflow over the surface makes a difference. As that water is exposed to the environment, it evaporates. If, before the concrete has become a solid, the water is able to leave the surface, we will get plastic shrinkage. Plastic shrinkage is characterized by, just as you see in the photographs, short, discontinuous cracks that are parallel to one another and are perpendicular to the direction that the wind was blowing in. And that is the dead giveaway. You can see the cracks there. They start up and they start, and they're not very straight. These occurred while the concrete was still plastic. The other thing that comes along with this is that we remove the water from the very surface paste, and as a consequence, it isn't very strong and it will dust forever. So these are the things that can occur. We get our high rate of evaporation, but the concrete is shrinking as we take this water away. In the second stage, after the surface water can no longer shrink to accommodate for that change, we then are going to see the water in the spaces in the concrete, in the pore spaces, that will flow to the surface and evaporate. And you will get a meniscus, just like you would from a straw that's sitting in water or any other capillary, where the water will evaporate and that meniscus, this meniscus down here, pulls the sides of the pore towards one another. And that shrinkage, as the walls of the pores are being pulled towards each other, is something that we need to be concerned about. Because if we don't take into account that shrinkage, we can have all sorts of problems. Then that third stage, as we said, we now have pockets of water that are available. They have to move through diffusion, and so it slows down the rate at which water is moving once again. The rate of drying, the rate that occurs, or the rate at which we encounter drying, is dependent on the quality of the cement paste, and as it usually is, that's tied to the water to cement ratio. The lower the water to cement ratio, the fewer pore volume that we have, and therefore the pores are smaller, and it makes it more difficult for diffusion to take place. The other thing that depends on or that the shrinkage depends on, is how much water was present in the beginning. Since if you have a low water to cement ratio but a very high cement content, you will increase that shrinkage. And so if you take concrete and put it in air at 50, 60, 70% relative humidity, after several months, the moisture content in the concrete will drop to 1 or 2% of its mass. And as that water leaves, the concrete has to shrink to accommodate the volume that's lost. And that shrinkage can present a major problem. We can calculate that if we know something about the absorption characteristics of the aggregate, how water is going to move by diffusion, the pore size, pore distribution, degree of hydration. All these sorts of things have an impact. And so what does our drying look like? And here are our 3 stages. We have a pretty constant drying rate when there's water sitting at the surface in stage 1. So there we need to be concerned. Stage 2, we have a diminishing rate because we're losing water, but it's getting harder for the water to get out. And then stage 3, it's becoming even harder for the water to get out. And so we have these 3 stages. We don't want these things to happen early. If they happen early when the concrete is not a very strong material, we are going to have a problem. And as a consequence, we're going to want to cure our concrete. And there are many definitions. This is the Portland Cement Association definition, is the maintenance of satisfactory moisture and temperature in the concrete for a sufficient amount of time that we develop the properties that we want. If you have a problem with curing, you are going to have a problem with the strength, with the volume stability, or that shrinkage we were talking about the permeability either to water or to salts, and of course the durability of the surface. So even if you have taken great care to make the right concrete, the right water to cement ratio and the right materials, if you don't cure it, if you don't prevent it from heating up or cooling down too much or for drying out, then you will not realize the properties that you have designed for. So what does that mean? There's a study that was done quite some time ago, almost 100 years ago, which looked at the effect of moist curing time on the strength gain of concrete. And that's shown in the curve. You should be aware that that is a logarithmic time scale, right? So it is showing, no, it's not. So that is a linear time scale, my fault. But it's showing when the ages were tested, 728, 90, 365. As you can see, concrete in the laboratory air for the entire time has a strength at about 30 megapascals. That occurs around somewhere between 28 and 90 days, and it has not changed at 365. If we cure for 7 days in water, then put it in the laboratory air, we get a similar behavior, but it occurs at a higher strength at 35 MPa. If we cure it for all 28 days, we're at 42 MPa. And if we moist cure it the entire time, you can see that the strength is about 45 MPa at around 90 days, but it has increased closer to 55 at 365 days. So these curves flatten out only when you start to pull water away from the system. So that curing is you have an adequate quantity of water that is around, and there's sufficient space for the hydration products to form into. So you can shut down hydration by having very, very low water to cement ratios, and you won't see any additional strength gain. But for the most part, the concretes we would encounter during normal construction, we're not going to have that problem. In addition to the temperature or the moisture effect, there is also a temperature effect. That temperature effect is that hydration will stop if the concrete drops much below 10 degrees C. And so you can see our conditions in the top figure, where you cast the concrete at different temperatures and you get different strengths. And those strengths are very dependent on maintaining both the temperature and the humidity conditions. If the concrete is dry and it gets re-wetted, then it will begin hydration again, but it's not the same as if it was kept moist continuously, because spaces in the concrete will dry out that you can't put water back into. So here's some additional data developed not that far away from here in Iowa back in the 1990s. And you can see the effect. If you cure concrete at high temperature, you will get an elevated strength at early ages and a decreased strength at later ages. If you cure it at lower temperatures, staying again above 10 degrees centigrade, then you will have a higher strength at later ages and a lower strength at early ages. Similarly, if you look at what that does in terms of strength, you get that increase from curing. But if you don't maintain the moisture, then you won't have this effect. And if you let the concrete drop below about 10 degrees, it doesn't do very much. Here's a good curve. It's looking at the curing temperature in terms of degrees C. And you can see that if you're at 10 degrees C curing temperature, you have a very low observed 7-day strength, but the highest 28-day strength. Similarly, at 50 degrees, you have the highest 1-day strength and the lowest 28-day strength. So that's why we try to aim at about 23, 24 degrees so that we're not too hot, not too cold, and like Goldilocks, we get to eat a whole bunch of bear food. What curing period is required? Like all good engineering questions, depends on what it is that we want the concrete to do. If we have a pozzolan, fly ash or slag that's going to be later reacting, then we're going to want to make sure that we extend our curing. If we have a type 3 cement that's very rapid reacting, we can get away with less curing and still have the same strength. The mixture proportions make a difference. If you have a moderate water to cement ratio, you don't need to cure as long as you would if you had a higher water to cement ratio or a lower water to cement ratio. What strength do you need? If you need to get all the strength that's possible, you may need to cure much longer than if you're using a 4,000 psi concrete, but you really only need 3,000. The size and shape of the member make a difference, something called the specific surface, which is the ratio between the surface and the volume. As that specific surface falls, you have more and more volume per unit area, then the impact of curing becomes less because the concrete at the surface will act as a curing blanket to provide water to the concrete below. The ambient conditions. If it's a moderate temperature, you do not need to cure as long as you might if it is very cold. And then the future exposure conditions. If your concrete is going to be exposed to, say, de-icing salts that are spread onto the pavement, you're going to want to cure it for a longer amount of time than you would if it's going to be used inside a warehouse, let's say, where there's no salt exposure. We also know that to prevent damage due to freezing and thawing, that concrete placed late in the year needs a chance to dry before its first exposure to salts. So let's take a look, see how I did. Lean mixes, but lean mixes being concrete mixtures that have very little cement in them, you may need several weeks. Rich mixtures, a few days. If you're in a plant, you can steam cure and get the 28-day strength in 12 hours under steam. Slabs on ground, it's structural concrete, minimum of 7 days, but if you use high early strength concrete, it may only be 3. How do we know? How can we do this? And one of the ways we can check, of course, is to use cylinders that are cured in the field under the same conditions as the member. So rather than casting a set of cylinders to judge the quality of the concrete delivered to the site, which we take back to the lab and handle in a systematic way, we could cast some cylinders and put them underneath the blankets. So we would know that if the cylinders are 4,000 psi and they were cured in the similar condition as the slab, then the slab is at least 4,000 psi. We can also do match curing. This is where equipment is set up that measures the temperature of the concrete member that's being cast, the footing or slab or wall or column, and then uses a control system to keep the cylinders at that temperature. And then we break those. We get a better estimate. We get a better estimate of what our strengths are. So, obviously, saying I'm going to cure it and maintain water is an easy thing to do. How do I do that? And there are 2 times you need to be concerned. The first is during placement. And that's where we talked about the plastic shrinkage and that stage 1 drying. And if it gets to stage 2 drying, then we start to have stresses in the plastic concrete. One way to avoid that is to fog upwind so that you increase the relative humidity. If it becomes close to 100, then your evaporation rate will drop to 0. If you go onto the App Store for Google or for Apple and search for hot weather concreting apps, you'll find that there are some that will estimate for you the rate of evaporation and tell you when you need to be fogging or not. For hardened concrete, so much of the curing depends on what materials we have available, what our method of construction is, what the ambient temperatures are, and what we really want the concrete to do when it's done curing. So one method we might use for curing, and it's a very old one and it's not used very much anymore, but it's still in the 100-year-old textbooks, is to cover the concrete with animal manure. Animal manure had enough moisture in it that it would dry out at the surface, but it wouldn't dry the concrete out. It stained the concrete terribly, but if that's what you were looking for, it works. Two real common ways of curing today. One of them is what we call a positive cure, where we supply additional water. So we take wet cloth or wet materials and put them on the surface, or we pond the water on the surface. The other is that we prevent evaporation. We put plastic sheeting on the concrete, or we spray it with basically a fancy paint that forms a film that prevents evaporation, a so-called curing compound. Now, the curing compounds, some of them are clear and some of them are white. And so the clear ones you're not really sure if you got them on completely, but the white ones will change the color and the appearance of the concrete. The shape and size of and location of the member, it's very easy to cure a slab by ponding it with a 1/4 of an inch of water. It's not so easy to cure a column that way, where you'd have to have the building height plus a 1/4 of an inch of water. Probably someone would notice if you flooded the site like that. And then for other aspects of where are we? Can we handle large water runoffs on our site? What about putting curing compound into the air? Is there any problems we would have locally if we had solid materials drifting through the air? And then, of course, like anything else, there's economics. The cheapest cure is to do nothing. Of course, that may give you all kinds of problems in the future. The best cure is to pond with water, but that may also be economically unfeasible. For example, if you are ponding water on the top of a bridge deck, that water quickly becomes relatively high in pH, and now you can't let it drip into the river. So it becomes something of an issue. Here's some pictures, right? We can supply additional moisture, a positive cure. And then you can see the lawn sprinklers keeping the burlap wet in figure 15.5. We could seal the mix in with water, that's our curing compounds, or we could fog, which will also seal the water in by changing the rate of evaporation, or going to accelerated curing. Here's a slab that is being ponded. And that slab has got water sitting on it, lots and lots of water, and that is going to be adequately cured. The problem here, of course, is that you have to maintain that water and control it, what have you. The other alternative, rather than a pond, is to spray down some material. And here you can see these are burlap sheets. You use cotton mats or rugs. All sorts of people make great things. You cannot begin curing too early from the point of view of maintaining water, but you can from the point of view of the surface appearance. If you put cloth on the concrete surface while the concrete surface is still soft, you run into a big problem. That big problem is that you will leave impressions of the cloth on the surface. You can put a polyethylene film down on top of the burlap to prevent evaporation, but if that has folds in it, you may discolor the concrete. And where the fold is, there's more oxygen, so you'll get a whiter color, and where the material is hard down and there's not very much oxygen, it will be darker, and that coloring will stay forever. There's some other ways, some of them older than others. You can pile soil, earth or sand, that's full of water on the surface. You can use sawdust. You can use wet hay or straw, and you have to be careful. Not only does that need to be held down in the case of wind, but can also start on fire due to decomposition. And most of these materials will leak something and stain the concrete surface. They're not very popular. Here's another one where we're curing or sealing the material in with white, opaque, semi-opaque sheets, and the sheets are overlapping. Here's a polyethylene film, and you can see the wrinkles that are present, and you see how it looks dark between the wrinkles, and the wrinkles are clearer. Surprisingly, that will occur, and that will show up. In the summer, if you're curing, you want to maintain the temperature low, you use white pigmented polyethylene. In the winter, where you can steal heat by radiation from the sun, you may want to use black. And then we have membrane forming curing compounds. You can see here we have a piece of runway that is being cured, and we're spraying on a white paint basically. It's going onto the damp surface, and that will hold water in and prevent evaporation. They come in several flavors. It could be waxes or resins, and waxes and resins are called dissipating cures. They, and exposed to ultraviolet light, they will fall apart. Or could be chlorinated rubber. Chlorinated rubber really forms a very nice membrane, but it's pretty tough to get off. Sometimes you will use something with a fugitive dye that stays visible until the material dries. Other times you want it clear or translucent so that you don't notice anything. And the advantage of white pigment, of course, is that it reduces the solar heat gain on sunny days. In every case, you have to be careful because you may end up putting on a material that acts as a paint, that is a bond breaker, and that later on you have to remove if you want to stick things to the slab, like sort of ceramic tile. So you want to be careful in those cases to ensure that you haven't added a colossal amount of problem for the next trade down the line. We can also accelerate the cure. We accelerate the cure by using moist heat, not dry heat. So moist heat, we would use, for example, steam, or heating coils that lie underneath blankets, or electrically heated forms or pads. And all of these are used locally in the winter to ensure that we don't let the concrete fall below 10 degrees and stop curing. There's a lot of people that have been working on internal curing. Internal curing is an absorbent aggregate that holds water within itself, or a polymer, the kind of polymers that you would find in baby diapers, or super absorbent polymers that they swell up when the water is exposed to them. If you put those in concrete, either the super absorbent polymer or the lightweight aggregate, that's aggregate with a lot of void in it, then that carries in water, and as the concrete around it dries, it will give up that water and give it back to satisfy the pressures that are generated by the evaporation of water, and so you can extend curing, and it's really quite effective. It can be quite expensive as well, and it has a detrimental impact on strength because you never get something for nothing. But internal curing is something that you're seeing more and more frequently. Minnesota is using it in bridge decks. One of the cheapest ways of maintaining moisture in the concrete is don't remove the forms prematurely. Now, if you have wood forms, you should sprinkle them a little bit, but steel forms won't let very much water through them at all. Where the concrete is exposed in the top, you need to keep water on there, and you have to remember that this will have the concrete hydrate in the absence of oxygen, and it will be darker than it would otherwise have been. Steam curing, very often seen in precast plants or operations where you're making the concrete as a hardened material, delivering it to the site. But you can steam cure in situ as well. Typically, you're using temperatures around 140 degrees Fahrenheit, and you track the temperature of the concrete, and once the concrete temperature is at 140, then you can turn off the steam, or else you're using the steam to cool things down. You do not want to get above about 160, about 70 degrees Fahrenheit, because you get reactions that you don't want that will lead to deterioration of the concrete. So what does a steam cure cycle look like? Initially, you have a ramp up period where you increase the temperature, at 10 to 20 degrees centigrade per hour. You then, once you've reached your desired target heat, you would hold that for some amount of time until you predict that you have reached your desired strength, and then you allow it to gradually cool. One of the things you can cause great damage by is putting a concrete in boiling water to accelerate its cure, and then take it out of the boiling water and put it in the laboratory air. And the surface cools down and the center stays hot, and you will crack it. You may not see the cracks, but the strengths will actually go down. So this is on the screen a typical steam curing environment. In the winter, we may not need to supply additional heat if we can capture the heat that's occurring due to hydration. And if you recall, we measured some of those heats of hydration. You can use insulating blankets, you can use insulating formwork, you can do all sorts of things to trap the heat in and passively heat the concrete by using that heat of hydration. We can also do electrical curing. We don't see this very much in North America, but it was a very popular method of curing in the Soviet Union and still is in Russia and some Eastern Bloc countries, where you would heat up the reinforcement the same way you use a highly resistive material to heat up a stove element, and it heats the concrete up. You can use the concrete itself as an electrical conductor, and that will heat it up. You can heat up blankets. Blankets have wires in them or tubes in them, and so those blankets will heat up. You can use tubing that you lay down across the surface. People often use it for snow melt or for thawing the ground, but if you put it on top of the concrete and put a layer of blankets over top of it, it will help you cure so long as there's water around. And then you can heat steel forms. And where you see heating of concrete that is not flat work, not slabs or sidewalks, it's almost always where you have a heater that's heating the steel forms, and then an insulation layer to prevent that heat from escaping anywhere else other than going directly into the concrete. Now, the curing compounds are sometimes referred to as sealing compounds. And curing and sealing are two different activities. Curing, as we've said, is the maintenance of temperature and moisture conditions to allow the reaction to go forward. Sealing is the placement of a material either on the surface or absorbed into the superficial pores in concrete that will prevent salts from getting in, or acid attack or abrasion or what have you. So a curing compound has to be applied immediately, as soon as it can be done without harming the concrete surface. A sealer or a sealing compound is best applied after 28 days. And so you see these materials that are sold as cure and seals. And of course they will cure or seal, but they can't do both, because if you put them on early on, then they're only good for curing, because hopefully you won't get any penetration into the pores because the pores are full of water. And then later you can use them as a sealer, because then they'll penetrate into the pores. But since you would require the pores to be both full of water and empty of water in order to be a cure and seal, no such thing exists. You can see film forming sealers, paints. They remain on the surface. Acrylic sealers, for example, acrylic paints, are a medium where you get a layer of acrylic plastic across the surface. And that's great stuff. It prevents, you'll see the water bead up on an acrylic. It'll prevent the absorption of grease and oil. You can also see penetrating sealers. Penetrating sealers are sealers that go inside the concrete. So, for example, boiled linseed oil and mineral spirits makes a terrific sealer. It will penetrate into the concrete pores so long as they're not already full of water down to a depth of 1/8 of an inch, and they will repel water. They work very nicely. But more commonly, we would see a silane or a siloxane. And the silanes and siloxanes are chemicals that if we put them onto the surface of the concrete here, end up with either a silane or a siloxane end on them attached to some big long hydrocarbon. And what essentially you get are these layers of hydrocarbon that are sticking up into the air, and the silica down here combines with the calcium hydroxide and it becomes a glue. And so you have this hairy slab at the microscopic level, and so if there's a big blob of oil, it sits supported away from the surface. It can't get to where it wants to cause you a problem, and you don't need to worry. So you'll see silanes and siloxanes. They're chemically active materials. They're surfactants, surface active materials, as opposed to linseed oil, which penetrates in, and then the voids can't fill with water because they're full of linseed oil and mineral spirits, and the water's not going to be very happy about that. One of the reasons that we need to cure our concrete is because we often rely very early on the strength. Even if we are not going to need our strength until 28 days according to the documents, we may find that we want to remove our forms and that the structural engineer or someone else is going to give us the guidance that says you can't remove the forms until you've reached 85% of the specified strength. 85% of the specified strength probably takes 3 weeks if you're going to hit the specified strength at 28 days. 3 weeks is a long time, and so often we design our concrete structure or other concrete mixtures, and our strength of concrete that we're putting in them is dependent not on what the specified strength is, but on an earlier age strength. For example, I want 4,000 psi at 28 days, but I want to remove my forms at 3 days, and I need 3,000 psi to do that. The 4,000 psi at 28 days, which is the contractual obligation, doesn't matter anymore because you will well exceed that so long as you are meeting the 3,000 psi at 3-day requirement. The faster you can remove the forms, the faster you can erect the next structure, the faster you build the building, and time is money. Also, the faster you erect the forms, the fewer sets of forms you have to buy. However, if the concrete has not gained strength and you strip the forms, you are going to permanently damage the surfaces in ways that cannot be repaired. So you need to know, and typically in a structural specification, the stripping strength, or the strength at which the forms can be removed, will be identified. Under normal moist curing and temperature conditions, concrete can reach 6 or 7 MPa, the types of strengths needed for removing the side forms. 24 hours for normal Portland cement, 12 to 14 for high early strength, 48 hours for low strength concretes that have a lot of pozzolans in them. Those are for thick sections. For beams and floor slabs, it could take up to 21 days. And so that's something that you want to work out with your concrete producer. Is not just what the 28-day strength requirement is, but also what the early age stripping requirements are. That's what I have to cover today for curing and sealing and a little bit of stripping formwork. I'm going to put an assignment up on Canvas as well. I'll get this presentation processed so that people can take a look at it. and then we'll have another reading assignment to reinforce some of these things, and a little quiz assignment. Any questions for either one of you? So assuming you're still there, you don't have any questions. So I'm going to stop recording, and then you should see something come in your Canvas feed sometime today. All right, take care, everyone.